Thank you very much for the kind introduction, and thanks for the invitation. It's very nice to be here. Exactly. I will talk about high-dimensional classification. And I usually gave this talk with only decision boundaries and noise, and today I'm also talking about margin. So it's something new. And the first slide is already a test for the projector, but I think it might work. So this is the problem that I'm talking about. So I want to do some classification. Yeah, what you can see here is my hometown. This is Berlin at night, and you see, okay, there's a little bit of a different in color, yeah, with the lighting. So these are the street lamps, and so in the former East, they're more reddish colored, and in West Berlin, they're a little bit more blue. And let's say I want to classify now which part of this image is West Berlin. Well, I have a lot of samples, which are these street lights, so I can try to find an area that corresponds to West Berlin by just looking where it's bright. But from this image, we also see a couple of these concepts that will reappear in this talk. So for example, there's a pretty sharp decision boundary right through the center, where the wall used to separate the east and west parts of Berlin. So there you really have to switch very quickly from one class to the other. There is some noise. So some lights in the east, for example, appear kind of blue. So they're wrong. This is noisy. And then, probably for me most interesting, I mean, there are lots of areas where there's sort of no light. So this is forest. And specifically here between East Germany, or former East Germany, sorry, and West Berlin, there's quite often just forest. So there's a bit of a margin between the two classes, because there we don't really need to, we could say we don't really need to classify that sharply, yeah, because there's a distance between the two distributions there. So we can make this all a little bit more mathematical. So I have some observations. These are usually called xi, sometimes capital, sometimes not. Xi and yi. So the xi's you can think of as locations. The yi are then labels. And in this talk, it's always binary. So the label is always 0 or 1. And then I'm looking for a prediction rule, and this prediction rule is supposed to be a function. I call it y hat here. And it should be a good function in the sense that it matches the distribution of the labels. So I want this thing that I call risk, this r, to be small. Yeah? So the risk is the probability of misclassifying. So y being the true distribution of labels, I want this y hat to match y most of the time. Okay. And if this is your setup, then there's actually a perfect way to classify. I mean, there are many perfect ways sometimes, but one of them would be to define a specific set, which I call here G star. And G star is the set where this kind of distribution here, okay, now, this thing, where the probability of observing the label 1 given your position x is larger or equal than 1/2. Okay, if I put everything in one set that satisfies this, and I'll take as a classifier this characteristic function of G star, then that's the best classifier. Yeah? So it corresponds to coloring your space into two colors. One is the label 1 region, and the other is the label 2 region. Okay. There are a couple of things that are interesting here. I already mentioned them. So that concepts that make this classification problem hard or not so hard, and they are basically these three here. Your possible set, the classification set G star, can be an easy set or can be a very complicated set. And if it's a complicated set, then the problem is harder. So here you see it, for example, in three classical examples. So this is just the iris data set where you classify flowers, and this is MNIST, but only zeros and ones. And the regions, so this one looks like a very simple region. This one looks like a bit more of a roughly shaped region. So this is a harder classification problem than this one, if we just think about regions. But then there's also noise. I mean, these data sets don't have any noise, so it's very hard to show you. but you could imagine this point to be wrongly classified, so on the wrong side of the decision boundary. So maybe you could also say that this problem is harder because it's a little bit noisy. And then there's this margin, and the margin basically says how far away are the two classes, or the probability, the densities, the mass of the two classes, is it separated? And in MNIST, you know, because MNIST is a very simple problem, they are quite well separated. So there's a lot of distance between the two. Okay, again, we want to make this more mathematical. And here are 3 conditions. So the first 2 I basically took from, and I'm afraid I forgot the reference here, but it's on the next slide, from works from Mammon and Tsibakov. So you take a kind of condition on complexity of your possible classification sets. And how do we do that? Well, we define some kind of entropy. Basically, I take some kind of reservoir of possible classes, sets that describe my classification regions, and then I define this sort of entropy. Here, it was classically this sort of bracketing entropy was used, which right now I don't really want to explain because I'm not going to use any of its properties later. But if you want to know, we can talk about it later. But you can actually think about just some kind of entropy that you, try to define an entropy on a set of sets, and it's probably going to be more like closely related to this. So it's just a type of entropy on a set of sets. So the distance here is the symmetric distance. But it's really not important that we understand this. The important bit is that this thing should now scale like delta to the minus r. So if we have a large parameter r, then we would say this is a very complex set because these entropies, they grow so fast with delta going to 0. If we have a small r, we would say it's a simple set of classification sets. Then we have this noise condition here. So again, one parameter, q. Basically, you're saying I have this conditional distribution, eta. So that's, again, the probability of observing 1 given some kind of position x. And it is really noisy when this eta is close to 1/2, because that's a point where you can observe both labels with the same probability. So that's quite noisy. But also, if you're close to 1/2, that would also correspond to a lot of noise. So this condition here tries to capture this. So how much mass is close to 1/2? Well, this should decay rather quickly. Yeah, so you have t to the power q. So if t is kind of small, then t to the power q is hopefully very small if q is large. So a large q corresponds to low noise. And then the last probability is this margin condition. And these are a little bit related, but they're still different because this is really a geometric condition. So I could say that I have, again, this density, and I defined before the correct classification region as essentially this set here, everything where eta is bounded by 1/2. Now the boundary of this is kind of the decision boundary. Once you go over it, you will be in the other class. And the probability of being close to this boundary, that should be small. Then you have a large margin. Yeah? So here you see the margin condition has two parameters, c and gamma. All the points that are close to this decision boundary by epsilon, there should be few of them. It should be epsilon to the gamma. So a large gamma means a large margin. Okay. Okay, with this you can now do learning. And there's already a well-established theory here. So this one doesn't actually look into margin yet. But this is a result by Mammon and Tsibakov. Basically, you can solve the classification problem really well if you just know the noise condition and the complexity condition. And you do it by empirical risk minimization, also something that we like. What you just need to do is you have your set of sets G. Okay, now first you need to find an epsilon net of this set. Yeah, so a bunch of other sets that are all a distance of epsilon apart. We call them n epsilon. And now I can just do empirical risk minimization over this net, which is given here. So I look at this set G in my subnet that best explains my observations. That's the empirical risk minimizer, and this is now the set that I want to use for classification. And if you set everything up just right, you get here worst case bound. So these are all possible joint probability distributions, and this is the risk of the solution of my empirical risk minimizer, and this is the best you could do, and it decays nicely. Now this is a complicated expression, but we can just have q go to infinity, so this first term will be 1, and this will be something like 2. So it's 1 divided by 2 plus r minus 1. So basically 1 divided by 1 plus r. That's a good rate if r is small. Maybe hard to accept for approximation theory people, but m to the minus 1 is a very, very good rate. It's the best rate. But if r is really large, then it's a slow rate. Okay, so this is the trade-off. The only problem here with this whole thing is that, of course, it's completely impractical. Nobody optimizes over epsilon nets of sets. So we actually cannot do it. We would just have to try all these different sets. Okay, that's not happening. And of course, that's also not what I want to talk about. So we want to do instead some kind of optimization that involves neural nets. Okay, so just very briefly, what is this neural network that I'm using today? It's the one that everyone always uses. So it's just a feed-forward neural net. My neural networks will be maps from RD to RNL. I have a certain input dimension, which is D. They're here. They can be deep, so they have a certain number of layers, which will always be denoted by large L. There's an activation function, which is called rho. I think in almost all results, that's going to be the so-called ReLU. And I have numbers of neurons per layer. So these are just the number of these dots here in each layer. And they are called N1 to NL. And then there are affine transforms, so TLs that map, well, one layer to the next. Yeah, so what really happens in the end is phi is this function. You have an input x. You first apply the first affine transform, then the activation function, affine transform, so on and so forth. Okay. So that's the setup. And the functions that I want to learn now, for them I also need to make an assumption. Yeah, so at the moment it was just this abstract set G that I'm learning. Okay, I need to make it a bit more precise, and I want to define my decision boundaries via some smoothness. So the smoothness that I'm using is reasonably straightforward. I mean, for image processing people, I think this would be natural to say this jump here also has a certain smoothness, classical smoothness. So right now, but this is only for this first part of the talk. I define my classifying functions. So you have to think of f1 as actually 0 and f2 as 1, but it holds also in more generality as these functions, and the boundary of that set B is locally smooth. That's what I want to assume. The decision boundary is locally smooth. Okay, so now we need to first approximate these functions, and then we need to learn them. And then we need to compare this to the optimal way of doing things. Okay, so first I have this rather old result by myself with Felix. So basically, if your set B has a smooth decision boundary, so some k continuous derivatives, then you can approximate it with neural nets really well. This discontinuous function here, this characteristic function of B, the classifier, you can approximate this really well if the boundary is smooth. So in particular, you can choose an M, large M, and then you will have a neural network that has only M parameters, and the error of this is going to be that. Yeah? So L2, the L2 error of approximating this function f scales like m to the minus k over 2d minus 1. So if you have a really smooth boundary, then even though this function is discontinuous, you can approximate it quite well. Yeah? Because neural networks can kind of resolve this discontinuity nicely. And the good thing is, in this result, the way we set it up, it also kind of intuitively shows you why you can approximate these smooth functions so well. You need deeper networks if the function gets smoother, because you, in a sense, need to resolve this discontinuity first. So locally resolve this discontinuity, and for that you need to create high orders of polynomials, which relates to this k. Okay. Now to learning. So unfortunately, we didn't do this. So someone did it before us. But they used our results, so that's pretty nice. So here are the two results by Kimon and Kim and Imaitsumi and Fukumitsu. So what they did is they're now training neural nets to solve this classification problem. And they do it using the hinge loss, which is just one choice. You could, to some extent, also replace this by another loss. But they did it for the hinge loss, and we will too. But the analysis is not so different if you do L2. And then you have a sample, xi, and labels yi. And if you make the assumptions that, okay, so there's a little error here. So actually, this is not true. So there could be noise, which is described by this noise condition. So x, y, and yi follow some probability distribution. Here I went a bit too fast. But anyway, if you assume what I just told you, your function has a ck smooth decision boundary, then they can show that the expected value of the error, of the risk of their empirical risk minimizer, so that's the minimizer of this thing up here, minus the best thing you could do, it scales like this expression. Again, not such a nice expression, but let q go to infinity, then you can remove all these q terms, so it's k divided by k plus d minus 1. Which is a nice number if k is really large. So if you have a smooth function, very smooth boundary, then you can learn this again close to an m to the minus 1 rate, which is pretty fast. Now you're using neural net, so you don't have to optimize over these kind of sets of sets. However, there is of course this d minus 1 term here, which is a curse of dimensionality. So if d is large, then this rate becomes really bad. And they also did something for margin. So now assume this margin condition. So there is not so much probability mass close to the boundary. Well, you have the following result. Again, you take this, the same function that you were optimizing over, this hinge loss, and you have data xi, yi, and you assume this margin condition. They came up with this result. So worst case performance over all functions with the ck discontinuity scales like this. It's essentially the same as before. There's just a small little gamma that is now there. And the gamma is pretty nice because it exactly affects this term that we didn't like, the large dimension. So if you choose your gamma like d, of course you cannot choose it, but let's say it would be the size of your dimension, then you would actually get rid of this dimension term here, which would be pretty good. So then you can approximate this thing essentially without curse of dimensionality, but then you would need to have this kind of potentially huge margin. I mean, if your dimension is like in applications 700, then you need a margin bound of 700, which is pretty high, margin exponent of 700. Okay, good. So now we need to find out how good this is. Then we'll find out that this is probably not that good, and then we'll try to do something else. Okay, so before I understand how good this is, I need to generalize a little bit. So let's not just look at functions that are locally ck, but locally anything. So I do this in the following way. I define these horizon functions. So just basically you have a high dimensional function, so it's defined on a d-dimensional cube, but its jump is the graph of a lower dimensional function. So in this case, you have a d minus 1 dimensional function, which is kind of the boundary function, and the horizon function is then just given as this thing here. So b of all the first, this should be an x, of the first coordinates is bounded, and this should be a d. It's bounded by the last coordinate. And then you can do this locally, so you have some set omega, and you just look at it locally, and if it locally is one of these functions, then you would say, okay, this is a function with, well, if your b's are from a set C, then you would say this is a function with C regular boundary. Okay, this is just a more general way of looking at these classifying functions. And to properly study them, of course, we need some kind of entropy. I already used that notion, but to make it more precise, I'm going to repeat it now. So we'll use this covering entropy of a set, mk, and then I have a distance function, which will usually be a metric here of some epsilon. And what is this? Well, you take a metric space. Oh yeah, so it is a metric. And you have a compact set k, and then you say, okay, I have an epsilon net, which is just a set inside of k, such that no point has a distance more than epsilon to one of the elements of this g epsilon. And the entropy is then just the logarithm of the smallest of these epsilon nets. Yeah, okay, there should be a space there. Okay, so this I need to describe a little bit the lower bounds that we're now developing. Okay, so here's a lower bound. Now we're trying to learn these horizon functions. For lower bounds, it's enough to look at the horizon functions. Yeah? I don't need to look at the full set of functions with a smooth boundary because this is a subset. So I'm only looking at horizon functions, and I try and figure out how well I can learn these. Okay, so this is here the set of all possible algorithms from my sample set, which is size m, to functions in my HC. And then I look at the worst case performance of these. So this is all H and HC. And this is the L2 error of the reconstructed function. And this will scale in the following sense. Yeah? So it's upper and lower bounded with these two parameters, m to the minus alpha over beta plus 1. And these alphas and betas, you get them by looking at the L1 entropy of the underlying set that describes the boundaries. Yeah? So if we know this thing, we know how hard our learning problem is. One thing that I need to mention is that for this lower bound, we assume that there's no noise. And that's a bit of a crucial assumption because as soon as you have just a little bit of noise on your labels, it's very easy to get some kind of lower bounds that are usually something like m to the minus 1/2. But since we say everything is correct, it's a little bit harder. And that's why we have this result. And here you see exactly this L1 entropy of the classification regularity set popping up. And the reason for this is kind of simple. So how we prove this is, well, we kind of set up a different problem that's just related to this. So we define specific densities that are just defined in such a way that the difference between the L2 norms of these H1 of our horizon functions is the squared Hellinger distance of those. And so this is just a specific construction of finding these densities. Okay, so we can find density that exactly satisfy this. And now let's look at this thing. So this is the L2 distance between the squared L2 distance between two horizon functions. But that's actually the same thing as the L1 distance between the boundary functions. Because if you look at two functions, I mean, you have two functions, you look at the distance between those two. The integral between the two, okay, that's the L1 norm. Now you just shift your perspective a little bit and you look from the top, then it's the L2 norm between the two horizon functions, because it's kind of just the measure between these two functions. So here you just need to shift your perspective a little bit to see this. But now, all these densities that we created here, the whole set of densities has now a packing entropy that is described by the L1 entropy of these, the classification set. And luckily, for this density estimation problem, in terms of squared Hellinger distance, there is already a result that gives us lower and upper bounds. We just need to know the entropy with respect to this Hellinger distance, but we can write it as the entropy of this L1. So that's how we get the lower bound. Okay, let's look at what this means. Okay, we can just plug everything in. For CK regular boundaries, like what this result from before was studying, we can find the L1 entropy. It's just epsilon to the minus k over d. And this would imply an optimal learning rate of m to the minus k over k plus and then d half plus 1/2. So their rate is actually a little bit worse. Yeah? So it misses this 1/2 factor around the dimension. But it's close to optimal, I would say, if d is not too large. And if d is very large, then both of these bounds tell us that learning is anyway impossible. Yeah, because you have a very strong curse of dimensionality there with the d in the denominator. So not only the rate that they had, but also every algorithm suffers from this curse of dimensionality. You could circumvent it in the margin case by just having a huge margin, but then the margin needs to grow like the dimension. Okay, so we wanted to find out now ways where you do not see this curse of dimensionality. And I already see Mario's eyes twitch, because of course this is going to be your favorite topic. I'm going to talk about Barron spaces now. So this is a way to, this is a function class that doesn't have a curse of dimensionality. So this Barron space, these are functions that have a bounded Fourier moment. So functions that, well, you take the Fourier transform, let's assume everything is well defined right now, and this multiplied with the argument, the integral is bounded by C. So that's the gamma C Barron class. And there's a second one that pops up sometimes, which is this RBV2 space. So it's also a set of functions that doesn't have a curse of dimensionality, kind of naturally arises in neural network optimization. If you do a point fitting problem, but you minimize with respect to the associated norm there, then all the solutions will be neural nets. So somehow it's meaningful. In any case, it's defined by the Radon transform. You take the Radon transform of f, and then you take a lot of derivatives in the radial direction, and then you compute the total variation norm of this. And if this is bounded, then you're in this RBV2 space. Okay. So these are, first one was introduced by Barron, second by Novak and Parhi. And so for these nice things hold, maybe we can show both theorems right away. So for Barron, you know, the approximation of a function in that Barron class, you can do with shallow neural nets, and the rate is going to be n to the minus 1/2, where n to the minus 1/2 is, of course, a horrible rate for approximation for everyone here, but it doesn't have a dimension in it, which is good. Yeah, so you need n neurons, and then you get this error. No dimension involved. And if you have f in RBV2, you have a similar result. Okay, here this is now with L infinity, which is slightly stronger, but in fact you could generalize this to L infinity as well. And then you get this rate, n to the minus d plus 3 over 2d. Has the disadvantage that now the dimension does appear, but the advantage that the dimension doesn't hurt. So it's essentially the same rate. Yeah? For large d, here you have more or less the same thing, 1/2. But for smaller d, then this second function class is apparently somewhat better. Okay, so my idea is now, okay, let's look at what happens if I take these functions as my decision boundary. Will it behave more like what we see in practice, that we don't have that strong curse of dimensionality? And what is the role of margin? Okay, so first let's do approximation. Again, let's say my boundary has this gamma C regular decision boundary. How well can I approximate a function, a classification function now with neural nets? I can do it quite well. I need a neural net with 4 layers. I have a certain number of neurons, let's say n, and then I can approximate the 0-1 loss. So that's the measure of everything that was classified incorrectly. And this scales like, okay, longer expression, but the important bit is n to the minus alpha half. Now I haven't told you what alpha is. It depends on the measure. So if the measure has a bounded density, then alpha is 1. So this is n to the minus 1/2. The same rate as what you had for Barron. If the measure is a really evil measure, that kind of you have a decision boundary and it puts all its mass, like with a pole, right on this decision boundary, then your life is a little bit harder. And then you get this alpha up here. Yeah, so if the pole close to the decision boundary is described by alpha, then you suffer this here. But let's assume that this doesn't happen. And it doesn't happen. Especially, the opposite of it happens if you have a margin, but we assume usually that, let's say, you have a bounded density, and then this is going to be nice. Okay, you can improve this rate slightly. If you take f in RBV, then you get this rate. It's essentially the same as before, now with the rate from the RBV functions. So in some sense, this, I think, is a very nice result, because the approximation rate, I mean, it's not fast, it's n to the minus 1/2, not fantastic, but it doesn't depend on the dimension, even though the underlying set could be discontinuous and super high dimensional. And the 0-1 loss is also extremely unforgiving, and we still get this kind of rate. So that's, to some extent, convincing. Now, what happens if you have a margin? Well, if you have a margin, then life suddenly becomes completely wonderful. Yeah, so let's say I take again Barron, gamma C regular decision boundary. I find a neural net, 4 layers, and so on and so forth, same size as before, more or less. If I also assume this margin condition, C gamma, then my approximation rate now suddenly is this. Okay, it's more or less like before, but the right-hand side is now n to the minus gamma half. So the approximation of this thing could be arbitrarily well. So if I have a large margin, gamma being, I don't know, 10, I have n to the minus 5. So that's a pretty good approximation rate if I'm looking at high-dimensional discontinuous functions. So now I can suddenly do arbitrarily well approximation. So fast, evil loss, high dimensionality, discontinuity, it works. So I can approximate a high-dimensional function, basically discontinuous high-dimensional function, basically like a low-dimensional smooth function, if I have the margin. Which isn't, I mean, it's not super surprising, of course, yeah, but that's what works in practice. So how does this affect learning? I first talk about the case where I don't have a margin. So here we do, again, learning results. Someone gives you samples and labels. You minimize an empirical risk, which is not specified here again, but it's, again, this hinge loss risk. We know exactly how to set up the neural net. That's described up there. So there's a certain size, a certain number of weights, certain amplitude of the weights that we need to enforce. And if you do all of this, then the error that you make in expectation scales like m to the minus 1 over 3. So that's the learning rate for Barron regular boundary. Again, it's important that there's no curse of dimensionality here, and we will see in a second that this rate is also quite close to our optimal rate. You can do something similar with the RBB boundary, but of course you only get like small improvement. Now, what happens when you do the margin? This is exactly the same setup as before, but now I assume that in addition, my density has a margin condition. And the rate that we end up with is now this. So the expected error of the whole thing scales like m to the minus gamma over gamma plus 2. So now there's really no dimension anymore. It's a learning rate without dimension, and it's a learning rate that if gamma is reasonably large, is m to the minus 1. Yeah, so high-dimensional classification problems, if there's sufficient margin, and the boundary is described by a nice function, you can learn completely without curse of dimensionality and with a fast rate. Okay. Of course, I made some assumptions to get there, but we will see in a second that they are not entirely unreasonable. And it seems like we can actually do classification in high dimensions. Good. I already mentioned this. There's no dependence on the dimension. I don't need to scale my gamma like the dimension anymore. Yeah, so it could have a high dimension, could have a small gamma. This would still hold. And we get the fast rates, m to the minus 1. Yes, please?
Can you remind me what the S is, please?
The S, oh, sorry. I didn't say that. So S is the sample. Yeah, so this is the expected value over the sample, which is IID chosen according to the underlying distribution. And this is the expected value that I'm taking here. Yeah, sorry. Yeah, it has size m. So this was maybe not specified here. So m is always the size of the sample. S is this sample. Yeah, and so it scales like the sample size to the minus, hopefully 1. Yes, please?
Do you have a control on the constant which is hidden behind this nest tilde?
Yeah, we have it, I think, precisely in the paper. I think we've spelled it out exactly. Yeah, there are some things that go into it. But in this case, not too many. So some probability, the only thing that could be quite large is if you really come up with a very weird function that needs to be covered with a lot of these horizon functions. That's the only thing that can really make your life hard, but you would need to try to build like a really funky set, because then you need to have a really large cover, and the size of this cover kind of linearly goes into there. But everything else I think is super tame, so there's no e to the d hidden in this constant. So there's no hidden dimension, exponential dimension dependence in there. Okay. Okay, so now let's compare this to the optimality. We can plug everything in without margin and find the best rate for learning these, let's say, these Barron functions, so this thing up here, so the best rate is this, yeah? Okay, we had 1/3. So for large d, we're exactly there, yeah? For large d, we have the optimal rate. If we have margin, then I unfortunately don't know the lower bound. So someone here would need to help me with that. Well, actually, I kind of know the lower bound, but I cannot prove it right now. But we can talk about this if someone wants to. But we can see that we are very fast if we have the margin. I don't know if we're optimal, but I think we're probably really close. Okay, this I already said before. We have this high dimension problem, discontinuity, and so on and so forth. Okay, so I have 9 more minutes to talk a little bit about what we tried to test this a little bit. Okay, so one thing, this is all pretty low dimensional, but we can already observe something. So what we did is we tried the problem of classifying things where we know now the decision boundaries, regularity. So we create lots of functions, and then we normalize them in the respective norms, L1, L infinity, Barron, RBB2, and C1, and then we try and find out how hard it is to train those. And we only do it in dimensions 2, 3, and 4, so it's still very low dimensional. But, well, let's see. So in 2D, we see that basically the error always decays in some sense, and C1 and Barron are more or less the same thing, and that's also true. I mean, their norms are on our set actually the same. I mean, the boundary function is then one-dimensional for one-dimensional functions, and the RBV performs best. But then if we increase the dimension, L infinity and L1 normalization, basically you cannot learn these functions anymore already. So this is already completely flat. So in high dimensions, there's no way you would learn those. If margin plays a role, I don't know. But in general, this will not be learnable at all. So these things do not describe our boundaries. And in high dimensions, you see also like C1 and high dimensions, so 4 dimensions, C1 and Barron separate. So Barron starts to become the better boundary function that still allows reasonably small errors at some point. And this RBV thing is surprisingly stable. It's always very, very good. Okay, but at least now you see that the regularity does make a big difference. Yeah? So if it's L1, it just doesn't work at all. If it's a smoothness-inducing norm or even like Barron, then you can still learn in 4D. Yeah? Okay, but 4D is not so interesting. We need to also go to higher dimensions. So we did some examples that can easily scale to super high dimensions. Of course, here I still only show you 3D. So we looked at classifying things that are inside and outside of a sphere, and then also put a margin there between those two things. So different types of margins we created. So these could be close or not so close, and you can scale this to high dimensions. Then you need to be a little bit careful, because everyone knows that the volume of the sphere scales a little bit funky. But if you take all of this into consideration, you get sort of nicely balanced sets. And then we can try to classify this problem in sort of any dimension. We did it in dimension 50 now, and what happens is that the results are perfectly aligned with the margin. I mean, this shouldn't be surprising, but it is what happens. So, of course, if you have a low margin, then you can, again, really not learn these things. Yeah, it's a super simple function. It's just find the inside of a sphere. We couldn't find a good solution if there's no margin. Yeah? But if the margin is 50, which is, of course, quite huge, then we get a really small error. You really need the margin to train these functions, to find these functions in high dimensions. So I would say this is probably, I would say the margin is probably more important than the regularity of the boundary. And then we also, I mean, this is all synthetic data. Of course, we also want to look at MNIST, but the problem is, for MNIST, we don't know the distribution, don't know the regularity of the decision boundary, and we also don't know the margin. So what are we even testing? So we were trying to create a margin that we know. And so what we did is we first trained a reasonably large neural net on training n test set. And then this is going to be something with an output that is a probability. So we can find a zero set of this, which is kind of relates to the decision boundary. And then we just look at the whole data set again, and it looks like this. So the original MNIST has a massive margin, which is why it's possible to do anything. I mean, here you don't see the form of the singularity, the decision boundary, just the distance to it. And everything is really far away from it. And then we try to make this into a problem with margin by creating lots of adversarial examples that kind of fill out the whole space. And we have different shades of margin for MNIST. And then we can compare those. And there again, you can see everything work quite nicely, almost like in our theory. So you have lots of lines in a log-log plot, and they have different slopes, which is really nice. And of course, they're ordered exactly according to the margin, which is nice. Yeah? So, and the largest one, gamma 50, is basically, I think this is still more data than the original MNIST. So MNIST is actually easier than this. But if you add all these points, then you get these rates. Yeah, so here it's cut off, which is unfortunate. So this is work of my PhD student, Jonathan Garcia. Okay, I still have 3 minutes. So I can conclude and then tell you something more afterwards. Yeah, as I said, classification is typically hard because this is a super high dimensional problem. Usually the highest we went was 700 dimensions because of MNIST. But of course, if you have real images, then it gets way beyond that. And usually you also have noise, which of course now I didn't really talk about that much because I was interested mostly in these in the margin, but you can see that also affected. And if you don't have a margin condition, then it's basically hopeless. Yeah? So most things that we tried, they don't work without a margin. But it could be simple. So if we do exactly as I told you, do empirical risk minimization over neural networks, then you can be close to the optimal thing that you could do, much better than just optimizing over sets of sets. If you assume something about the boundaries, which is in this case Baron or RBV, could say that that's arbitrary, but if you look at the other lower bounds, you see that with classical smoothness, it just couldn't be the case. It just couldn't work. If you have low noise, that's usually good, and if you have this margin condition. Then you can usually get close to this m to the minus 1, which is a fantastic rate. In fact, it's the best thing you could ever do. Okay. Oh, sorry. So we just want to say very briefly where this is from. So this is the original manuscript on the approximation of function with smooth boundary. Here we extended everything to Baron. These next two works are the very nice papers by Kimon and Kim and Imaitsumi and Fukumitsu, which extended our work to the learning regime. And that's actually where we learned all of this from. And then the last two are the generalizations that I talked about today. So this thing is generalizing everything to these RBV2 functions, which sounds completely trivial, but unfortunately, in the original paper, they didn't estimate one quantity, which is incredibly crucial, and so we had to do all of their computations again. And the second thing is the work on margin, which is not yet done, but it's on my laptop, and it should be done basically this week, if I find some time, but I probably won't. Okay, so that's all I want to say. Thank you very much for your attention.